So the first one is, so we have to compute the chromatic polynomial of the following graph. Suppose I have this graph. So there are four vertices. So what will be the chromatic polynomial? Let me try it. So this is my graph. So I have to find this g comma k. So there are k colors, right?
Yeah. It will be.
So let me name the vertices. Yes.
So k k minus one.
Right. So this one has k choices. Then
Yeah. K minus one, k minus two.
okay.
Yeah. K minus. It's also k. Yeah.
No, k minus one, right? Because it cannot have the same color as this one, right?
K minus one. Okay. Yeah.
Right. K minus one, right? So hence, so this is k into k minus one square, k minus two, right? Okay. What about this one?
Let's see.
Yes. So there are five vertices. Yes. Tell.
K minus one.
Right. So this is k.
K minus one. K.
Okay. So
And
this
number three. Number four. Number three is K.
not k, right? Because it cannot have same as that of two, right?
Eh, two is K minus one, so three is K. Is right.
No, no. It is like this, right? So this has k minus one choices, right?
Uh,
So three has k minus one choices because it cannot have the same color that of
ah,
uh right.
I'm confused about another. So K minus one. Yeah.
Right. Now four.
Yeah. K why K minus two. Yeah.
Right. K minus two because it cannot have the same as two and three. Right.
And K minus two again.
Right. So this is k minus two. Yes. But now we can have slightly different one, right? So for example, so it can happen that so okay we can color it in a different way. So this is one coloring where these
Mm,
two things are different, this 1 and 4. So
mm,
these two are different, right? So but suppose we take the same thing.
mm,
So it can happen that 1 and 4, so this can have the same color, right?
mm. So
Right.
it's K.
Yes, so we'll do a different way. Right. So now suppose it has k choices and this also have k choices, right?
Yeah.
Now this has k minus one choices, this also have k minus one choices, right? Because 2 and 5 I can color
Yeah.
like this, right?
Yeah, I think so. I think we should do in the second 1, 2, 4, 5, and the last is 3.
Yes, so now 3 is two from different from 2 and 4, so that is k minus 2, right?
Mm,
So from here what we get is the polynomial is, so k square into k minus 1
mm,
into k minus 2, right?
K
So
minus,
this is the case where these
K
two
minus
things.
1 square.
Yes, still.
Oh, K minus 1 square.
Yes, yes, k minus 1 square. Yes, so this is the way. So this is a valid way of doing the color, right? So this will be the result. Actual, this will be the polynomial, right?
Mm. Yeah, yeah. It's
Okay.
okay. Mm.
So now next one is so saying that use chromatic recurrence to obtain the chromatic polynomial of every tree with n vertices, right? So what it is saying is, so the chromatic recurrence we can use to find the so chromatic recurrence we studied, right? So this one. Mm, yes, so this one, right? So the recurrence is using the age deletion and age contraction. So there is one recurrence we learned, right?
Mm.
Right. So we'll use that to find the chromatic polynomial for any tree with n vertices. So let us see. So the proof we'll use by induction on n. N is the number of vertices. Okay.
Mm.
So n equals to 1, it is true, right? So the polynomial is k. Right. So the claim is so this chromatic polynomial will be k into k minus 1 to the power n minus 1. So this is the claim. So now
Mm.
the result is true for n equals to 1, right? It is there is only one vertex and it can be colored in k ways, right?
Mm.
Fine.
Mm. 3. Mm.
Right. So now
Mm.
if we contract an edge, so contracting an edge of an n vertex tree, so it leaves a tree with n minus 1 vertices, right?
Mm.
And if we delete an edge, so deleting the edge leaves a forest of two trees. So if we delete any edge, then the tree was connected, but now it becomes disconnected, and there is two trees, right,
Mm.
with order m and n minus m for some m
Mm.
between 1 and n minus 1, right? So if the so let us see an example.
Mm.
So suppose we have the tree like this, right? So now suppose I delete this particular edge.
Mm.
Suppose I delete this edge, right? So
Mm.
then what is the resulting tree? So the resulting thing is two trees, right? So this will
Mm.
be and this. So this is a forest that has two trees, The
mm,
original thing was 1, 2, 3, 4, 5, 6, 7, 8. N equals to 8, right?
mm,
N equals to 8 was there. And now it is 1, 2, 3, 4. So m is 4 and 1, 2, 3, 4. So this n minus m is also 4.
mm,
So deleting an edge leaves the forest with two trees of order n and n minus m respectively, right?
mm. Yeah, yeah. Mm,
Right. And this is the thing. And if we contract, so if we contract an edge, then if I contract this one, then this vertex and this vertex get merged, right?
mm,
So
mm,
then we will have n minus 1 vertices. So it will be 7, right?
mm.
Fine.
Yeah, yeah, yeah. Mm,
Right. Now we can use the induction hypothesis for both of them, right? So if we use the induction hypothesis, and the chromatic recurrence relation, right? So what will happen is, so the chromatic, so this with k is nothing but g minus e k
mm,
and minus, so g dot e, right, with k, right?
mm,
So now, so g minus e, so when we delete, it has two factors. It has two trees, so it will be that is one with order m, so k into k minus 1 to the power m minus 1, so that is for the first tree,
mm,
times for the second tree I have n minus m, that is order, so k into k minus 1
mm.
n minus m minus 1, right, by induction,
Yeah, yeah. Mm,
minus now g dot e has order n minus 1, so it will be k into k minus 1 n minus 1 minus 1, right?
mm.
So now if we bring them together, so I have k square into k minus 1 to the power, how much will be that?
Minus one, so 8 minus 2.
Right, n minus 2 minus k into n minus 2, right?
Mm,
So we can take this k into n minus 2 common, then we have k minus 1, right?
mm,
N minus 1. So this is, so we have done using induction.
mm.
Fine.
Yeah, yeah.
Okay.
Mm,
So the next one is, so prove that, so k power 4 minus 4k cube plus 3k square is not a chromatic polynomial.
mm.
So what does it mean is, so you cannot actually have a graph
Yeah, yeah.
that has a chromatic polynomial like this, right?
Mm. Yeah, got it. Mm,
Yes. So yes, so if you recall, so whenever I have, so in the chromatic polynomial of any graph, the highest degree is the number of vertices, right? So the degree is equals to the number of vertices, and the second coefficient, is minus the number of edges, right?
Yeah, yeah, yeah.
So from the polynomial, what I get is the n
Mm.
is 4,
Oh,
and the number of edges is also 4,
oh, oh.
right?
The degree, not degree, the height decrease, right?
Yes, yes, highest degree. Highest degree means a degree of a polynomial means highest degree only.
N is the number of vertices.
Yes, yes,
N is the number of vertices.
yes. So suppose it is a
Okay, 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 I got what it the degree of
yes, yes,
polynomial.
yes,
I
yes.
the degree of some vertices. Yeah, okay, okay.
No, no, no. Degree of this.
Okay. Yeah.
Yes.
Okay.
So this is 4, and number of edges is also 4.
But
So now,
we have some.
yes.
Mm,
Uh, right. So this is 4, but there are only two graphs. So
it's for
the only such graph, or you can do only graphs with 4 vertices and 4 edges are these are the only graphs. So either you have a cycle
mm,
with 4 vertices,
mm,
or you have this graph, that this triangle with a single edge. So only these two graphs are possible, right? Any other graph possible?
mm,
Can you think of
mm,
with 4 vertices and 4 edges?
mm, mm,
So there are only these two graphs are possible. So this is C4, and this is called the PO graph. But we have computed the chromatic polynomial for each of them.
mm,
So for this one, the chromatic polynomial is k into k minus 1,
mm,
k square minus 3k plus 3. And this one we just computed. So it is
mm,
k into k minus 1 whole square into k minus 2.
mm.
But none of them matches with this if we expand.
Yeah, yeah, yeah. Mm,
So it cannot be a chromatic polynomial of any graph.
mm.
Fine.
Yeah, it's okay.
Right. The next one is, so prove that. So the chromatic polynomial of the cycle for any n. So this is given by k minus 1 whole power n plus minus 1 to the power n times k minus 1.
CN. Mm,
Right.
CN. Mm, CN. Mm. So we can use induction.
Yes, yes. So we can use induction on the number of vertices. Okay.
Uh,
So since it is a cycle, it starts from 3, right? N has to
mm,
be greater than equals to 3, right?
yeah, three.
So we use induction line, right? So the first base case is
Mm,
n equals to 3, right? So if I have a 3 cycle, right? So then what is the chromatic polynomial? So this is k choices. This is k minus 1 and this is k minus 2, right?
mm,
So for C3 k, this is k into k minus 1, k minus 2, right? Now we have to check whether it is matching with the given formula. So now this is the left hand side. The right hand side is k minus 1 whole cube plus, right?
mm,
So we have to verify whether it is working. So it is,
mm,
so we can take k minus 1 common,
mm,
minus 1, right?
mm. Oh, yeah, it should be matching.
So how much we are getting? So it is k into k minus 2.
Mm.
So this is matching, right?
Yeah,
So
yeah.
true for n equals to 3. So now suppose we assume that it is true for maybe n minus 1, and then we prove for n, right?
Mm,
Okay. So
yeah.
now we can use the chromatic recurrence formula. So
Ah, ah,
for larger n, right? The chromatic recurrence formula,
delete one. Log one.
right? So one is it deletion and one is contraction, right?
Mm,
So Cn with k is chromatic number of Cn minus one edge and minus the chromatic number of Cn with contracting one edge and k. Right. Now we have to identify what is this graph. So if we delete one edge, then what happens?
let's see the bug.
Yes. So this is a path. Number of vertices remain same, and if we contract, then what happens?
Let's see the n minus one.
Right.
Cn one.
So it becomes a cycle, but size becomes n minus one.
Yeah.
Right. So now for path, uh, what is the chromatic number? Because path is a tree, right?
Mm.
So we can use the formula for tree we just computed. So yes,
One.
so
Okay.
tree is k into k minus one to the power n minus one. So that we can use.
Okay.
So this is k into k minus one to the power n minus one. And for cycle, we can use the induction, right?
Mm.
So it is n minus one. So k minus one to the power n minus one. Then plus minus 1 to the power n minus 1 times k minus 1,
Mm.
right?
Yeah, yeah.
Right. So now let us simplify it.
Minute one. Yeah. Um, we have 3 minutes.
So then when minus comes, it will become n, right?
Oh,
Fine.
yeah, yeah, yeah.
Now
Fine.
from this first two terms, if I take k minus 1 to the power n minus 1 common,
Uh,
right? So then I have another k minus 1, right? So it will become k minus 1 to the power n. Fine.
oh, y k minus one minus k minus one.
Right. So here both of the terms are common, right? So if we take out k minus 1 to the power n minus 1, I have k and
Ah, okay,
minus
okay, okay.
1,
Ah, okay, 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 okay. Fine.
right? So I think this is fine. Fine, right?
I said it's okay. No, no
Okay.
confusion.
So
No.
now the thing is, okay. So the next one is, so it is a part B. Okay. So suppose H is another graph. So H is a graph which is G joined with K1. K1 is just an isolated vertex, right?
Mm.
So now we have to prove that mm, the chromatic polynomial of H is actually same as the chromatic polynomial of, or K times the chromatic polynomial of, 1 minute, let me check. Yes, K times the chromatic polynomial of G along with K minus 1.
Mm.
So how to do it?
Union with K1.
Yes, G join with a K1. So join is so this thing, right? So the K1 is just an isolated vertex. So suppose this is my G, right? And suppose this is one extra vertex, and I am joining with
Ah,
all
okay.
the vertices of G,
K1. Okay.
right? So how to prove this one?
equal to K, C, K minus 1, S, mm,
Yes, how to do it?
K, C, K minus 1. I think we can use, oh no, we cannot use recurrent, then K. Uh,
Okay.
uh,
So the thing is,
that's is right because the one outside we
right, right,
color K, so we have remain K minus 1.
right, right. So the outside is K. We
Mhm.
can color it in K ways. Now the remaining graph I can color it in K minus one. So I have to use K minus one colors, right?
Yeah, yeah,
So directly it follows, right?
yeah, yeah.
So chromatic number of, okay. So this one is follows. But why this particular observation is, so if I choose Cn as my original graph, okay.
CN.
So instead of G, so if I take Cn, that is the cycle,
Mm,
right? Then
yeah.
what happens? So then the chromatic polynomial of Cn join K1. So this is nothing but by definition I have Cn with K minus 1, right?
Mm,
So but now I know what is the chromatic polynomial of Cn by this formula, right?
mm,
So this will actually help us to find the chromatic polynomial of the join thing, right? So that's why this formula is helpful. So
mm,
if I know the polynomial of G and suppose H, the my graph is I can express like this, then it is easy to calculate, right?
mm.
Fine.
Yeah, yeah. But it's just a special thing.
Yes, yes, yeah. So it is just a special formula, yes, but
Mm,
sometimes it is helpful,
yeah, yeah. Mm,
right? Okay. So the next one is, so now suppose n is greater than equals to 1 and gn equals to suppose a path with Cartesian product with k2, right?
mm,
So how does it looks like first of all? So it is, suppose I have a path like this and another path, right? And I join like this. So this is the ladder type of thing. So this is my graph, Pn Cartesian product with k2, right?
mm,
So it has 2n vertices and 3n minus 2 edges. Fine.
mm,
So the question is, so prove that the chromatic number of this Gn is nothing but k square minus 3k plus 3 whole power n minus 1 times k into k minus 1. So this we have to prove.
Two in mm. K2 is S on it only is right.
Yes, yes, k2
K2.
is a single edge.
K2 is
Yes, sir.
K2 K2 is two vertices is right and one S.
Yes, yes, two vertex and one edge.
So K2 and B2 is the same.
K2, yes, yes, K2 and P2 is same.
Okay. Okay. Yeah. K2, B2 and the same. Yeah. And so this is N N two.
Right. So how to do it?
Mm, Gene. So we
So
should in induction in N.
induction, yes, we can try induction.
Uh,
So okay, so let us try.
yeah.
So if n equals to one, then what happens? What is the figure?
B N.
So right. So let us check. So proof by induction one. Suppose n equals to one. So then G1 is nothing but P1 join with K2.
Mm,
So it has two n vertices. So that means two vertices and edge, right? So this is the graph G1, right?
mm. Two. What is CG1? Oh.
G1 is P1 join K2. Then this is the only graph because if you see it matches with the number of vertices and number of edges, right?
Mm,
Fine.
mm,
So this I know the chromatic polynomial. So this is k into k minus 1, right? So the chromatic polynomial of G1 and k, that is k into k minus 1, right? So now I have to verify whether it is working or not. So if I put n equals to 1 here, so it is gone, right?
mm,
I am left with k into k minus 1, so it is working, right?
mm,
So now if I take, now we have to prove for the bigger things. So suppose n is strictly greater than 1, right? And now we can use the recurrence relation. So the chromatic number of G and K.
mm, mm,
So that is nothing but chromatic number of Gn minus some edge minus chromatic number of Gn contraction with edge and K. Right. Now we can choose which edge we want to do. So suppose let us choose this last edge. Right.
mm.
So
F N E S. Yeah, yeah.
yes, any edge we can do. So let us, if I choose this large last edge as my
Mm,
edge E, right?
mm,
So then after contraction, okay, first of all, let us check after deletion what happens. So if
mm,
I delete this one, so then what I am left with? I am left with up to this one is Gn minus 1, right?
mm,
And two edges are left with these two vertices, right?
mm. Yeah.
Fine.
Yeah, yeah.
So how many, what will be the chromatic number?
N minus G N minus 1 K.
So
G. Mm,
whatever is coloring up to this one is done. Then this vertex I can color in k minus one ways, right? Because it will be just different from this one, right?
mm,
And this vertex I can color in k minus one ways. It will be different from this one, right?
mm, mm,
So this will be nothing but chromatic number of g n minus one comma k times the for the last two vertices k minus one whole square, right?
mm. Yeah, 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 yeah.
And now if I contract this one, so if I contract this one, so then it will look like this one, right?
Yeah, 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 yeah.
So if I contract this one, so then it will look like this one,
K minus 2.
right? So
No, no. K minus 1 or K minus 2.
yes, it's k minus 2, right? Because
Okay,
up
okay.
to
Yeah,
this one is gn minus 1,
yeah, yeah, yeah.
then I have to color this one different from this and this, so it
Mm,
will be k minus 2, right?
mm,
So this will be chromatic number of g n minus 1 comma k times k minus 2. right?
Mm. Yeah.
So now both of them has the first part common.
Mm.
So n minus 1 or comma k. So times k minus 1 whole square minus k minus 2, right?
Mm.
So how much is that? So this part is, so k square minus 2k plus 1 minus k minus 2,
Mm.
right?
Okay. Minus two.
So k square minus 3k.
Minus one.
Sorry, this is plus 2, plus 3,
Minus three. Yeah.
right? So and this part is by induction, I know. So by induction it will be this part, right?
Mm.
So
Yeah. So that's it.
yes, so that is actually matching. So this one is
Mm. Mm. Okay. Minus two.
right. So only it will become n minus
Mm.
2 here
Mm.
because it is n minus 1. So
Mm.
so now we have to just multiply.
Mm.
So it will be nothing but so this will become k square minus 3k plus 3 whole
Mm.
power n minus 1 times k into k minus 1.
Mm.
Fine.
Yeah. It's okay. Mm.
Okay. So maybe we'll stop here then.
Yeah. Yeah.